Dear students, we have seen inner definition of inner product and few examples, and causes squares inequality, triangle inequality. A vector space V with some function usually written like this is called inner product space if this function satisfies those four conditions for every ordered pair of vertices in V. Then we call this as a inner product space. Whenever I say Fn, always note that Fn is a inner product space with respect to the standard inner product. Whenever I say Fn, the inner product space Fn, then assume that this is the standard inner product. Whenever I say this one is an inner product space, then assume that Frobenius inner product. Morning, we have seen Cauchy-Schwarz inequality. What is Cauchy-Schwarz inequality? What is inequality? It is modulus of inner product of x comma y. This is less than or equal to norm x into norm y. Let us see the same inequality in this inner product space. Let x is equal to a1, a2, etc. an, and y is equal to b1, b2, etc. bn are in V. Let this belong to V, and here the inner product we know. What is the inner product? The standard inner product summation ai bi bar. So inner product of this left hand side will be modulus of what is the inner product? Summation ai bi bar. I runs from 1 to n. This is less than or equal to norm x. Norm x square means we don't need square root. Norm x means we need square root, and norm x means square root of inner product of x comma x. So that will be summation modulus of ai the whole square. I runs from 1 to n whole to the power 1 by 2, and into summation I varies from 1 to n modulus of pi square whole to the power 1 by 2. This is called the Cauchy-Schwarz inequality form in Fm. Similarly, triangle inequality. We have seen the triangle inequality. The triangle inequality is, what is the triangle inequality? Norm x plus y is less than or equal to norm x plus norm y. This is a triangle inequality. The same triangle inequality becomes like summation ai plus bi the whole square whole to the power 1 by 2. I runs from 1 to n is less than or equal to summation mod ai square whole to the power 1 by 2 summation mod bi square whole to the power 1 by 2. Here instead of x plus y, ai plus bi, it is norm. So if you take inner product of x plus y comma x plus y, we will get modulus square. There is no square here, so the whole to the power 1 by 2. So this is the triangle inequality in Fn. In schools we have studied that inner product of x comma y is equal to norm x norm y cos theta. Okay, so if you take modulus, it is already non-negative, so if you put modulus here, we will get the inequality. We will get the inequality less than or equal to norm x plus into norm y. Since this cos theta is always less than or equal to 1, Now we are going to see a new definition called orthogonality. When do we say two vectors are orthogonal? If the dot product between two vectors is 0, then we say that two vectors are perpendicular, right? So now we are going to say orthogonal. Instead of perpendicularity, we are going to say orthogonal definition. Let V be an inner product space for x comma y in V. If the inner product is 0, then we call x is orthogonal. X is orthogonal to y. That is, x is perpendicular to y. X is perpendicular to y. If the inner product is 0, then we call those two vectors are perpendicular to each other. Now let us see what is unit vector. Unit vector. If norm x is equal to 1, then we call x as a unit vector. Then x is called an unit vector. A set of vectors v1, v2, etc. vk is called an orthogonal set. Orthogonal set. If inner product of vi comma vj is equal to 0 for I is not equal to j, for r I comma j. This set is said to be orthogonal set if every vector is orthogonal to the other vector. For example, in R3, x-axis, y-axis and z-axis, those three vectors, those three axes will be perpendicular to each other, right? So if we consider 1 comma 0 comma 0 and 0 comma 1 comma 0, 0 comma 0 comma 1, or otherwise take 2, even 4, 5. So this is an orthogonal set. This set is an orthogonal set because every vector is perpendicular to other vector. Now orthonormal set. Orthonormal means that has to be orthogonal as well as each vector has to be a unit vector. Orthonormal set definition. These are all definitions. A set S is said to be orthonormal if S must be orthogonal and then every vector of this set must be a unit vector. Then we call this as an orthonormal set. This is not orthonormal, but consider this set S1. This one 1 comma 0 comma 0 and E2. What is E2? 0 comma 1 comma 0 and E3 0 comma 0 comma 1. This is these three vectors. Every vector is orthogonal to another vector and each one is a unit vector. So this is an orthonormal set. Suppose a vector is not a unit vector. How to not a unit vector? For example, we can take any vector. Take any non-zero vector in the vector space V. Any non-zero vector. Consider V. V is equal to x by norm x. See here, I am dividing x by its norm. I am dividing the vector x by its norm. Okay, now find norm V. Norm V is equal to norm of this one. What is that one? 1 by norm x into x. It's just a number, right? So norm Cx is equal to modulus C. here this is the model. It's a positive non-negative, so we don't need modulus into norm x. So these two get cancels, we get 1. So norm b is 1. So what we get is, if you take any non-zero vector and if you define that vector by its norm, we get a unit vector. This process is called normalizing. That is, dividing any non-zero vector by its norm is called normalizing. Dividing any non-zero vector by its norm is called normalizing. See, this set is an orthogonal set. If you take any dot product between any two vectors, you will get 0. So it's an orthogonal set, but it is not a unit vector. So this is not orthonormal set. It is not orthonormal set. So we now consider a new set. Let us say it is S1. What is its norm? Norm is equal to square root of inner product of x comma x. So we get 2 square plus 2 square plus 0. So square root of 8. This is norm. This vector's norm is square root of 2. This vector's norm is square root of 9. That is equal to 3. So now divide this vector by its norm. 2 by square root of 8. 2 by square root of 8 comma 0. 1 by square root of 2 minus 1 by square root of 2 comma 0 and 0 comma 0 comma 3 by 3 is 1. Now consider this new set. This set is orthonormal set. What I have done is, I have divided, it's an orthogonal set. We have divided each vector by its norm. See, you have to be clear about a norm. What is its norm? What is the norm x? Norm x is equal to summation mod a square whole power 1 by 2. So its norm is summation. So instead of summation we can directly write 4 plus 0 and whole power 1 by 2. That is square root. So we have got this one. This is the standard inner product. That's why we have got this one. Now consider the following set. H is equal to set of all continuous functions defined on the interval 0, 2 pi to complex plane. These are all continuous functions. Set of all continuous functions from here to C. This is a vector space over the complex plane. This is a vector space. Verify. Now define an inner product here. Let f and g belong to H. Define an inner product between f and g as 1 by 2 pi integral 0 to 2 pi f of t into g of t whole bar dt. Now define an inner product like this on this set. This inner product, this definition, this one becomes an inner product with respect to definition. So this becomes an inner product. This is an important inner product, and you may see that this is the generalization of the standard inner product. Summation, instead of summation we have got integration. Instead of a f of t, instead of ba bar g of t bar. This is some normalizing factor. We shall see later. Okay, it's a complex variety function f. So f can be written as f1 plus I f2. It is a real part of f. This is the imaginary part of f. Similarly, note that integral f, the whole bar is equal to integral f bar, and try to prove yourself that this is an inner product. Now let us see orthogonality on this set H. Now let fm of t is equal to e to the power int. So fn of t is equal to e to the power int. So what is fn of t the whole bar? This is equal to e power int the whole bar. E power I theta is equal to cos theta plus I sin theta. Okay, cos theta plus I sin theta. So cos theta plus I sin theta, the whole bar is cos theta minus I sin theta. So this is equal to e to the power minus int. How? E power I theta, the whole bar is equal to e to the power minus I theta. That's why. Now consider this inner product. Inner product of fm of t comma fn of t. Okay. Let m and n are different, distinct. What is the definition? Now we are talking on this vector space H. What is the inner product is given? 1 by 2 pi, integral 0 to 2 pi. What is fm of t? E power I m t. What is g of t here? Actually fn of t is this one. So g of t bar. So fn of t the whole bar is e power minus int dt. So this is equal to 1 by 2 pi into e to the power I m minus nt by I times m minus n integral 0 to 2 pi. If we apply the upper limit, we will most importantly m and n are integers, where m and n are integers. See here, if you apply 2 pi, we will get e to the power I times some integer times t. Okay, if you apply 0, we will get it is 1. Anyway, e power I times some even number of t, that is, if you apply the upper limit, we will get some, instead of t, if you apply upper limit, we will get e to the power I, this integer into 2. So some 2k pi. If you apply 0, it is 1. Anyway, if you apply upper and both lower limit here, you will get it is 1 only. The numerator will be 1 only. But when you apply the lower limit, you will get some minus of the lower limit. So this will be equal to 0. So what we have got is these two are orthogonal. These two are orthogonal. These two are perpendicular to each other. These two are perpendicular to each other. So what happens if both are same? If both are same, then these two get cancels. We will get this is equal to 1. So what we have got is inner product of fm of t comma fn of t. This is equal to 0 if m and n are distinct, and this is equal to 1 when both are same. So this is equal to delta mn. What is delta mn? This is equal to 1 if m is equal to n, otherwise 0 is drag delta function. So here see, in R3 you may have seen E1, E2, E3. This is an orthonormal basis, right? This is a basis for R3. This is a basis for R3, and this is orthogonal as well as unit vectors. So this is an orthonormal basis for R3. For R3, this is an orthonormal basis. Similarly, see, for this vector space, with respect to this definition, for this inner product space, now we have seen EIMT, e to the power IMT, e to the power INT. These set of functions, these forms, if m and n are distinct, we get 0. And if they are same, we get 1 unit vectors. So what we get is, this is what? This is equal to norm fn of t the whole square, right? So set of all fm of t, where m belongs to z, these are all this is an orthonormal set. This is an orthonormal set for this vector space. Because these are all orthogonal to each other if m is not equal to n, and also unit vectors. So this is an orthonormal set. Moreover, this forms a basis for H. That's why we could write every continuous functions as a Fourier series, complex form of the Fourier series. We could write every continuous function as a complex form of the Fourier series, right? That means here every vector in R3 can be written as a combination of these three vectors. Similarly, since this forms a vector space, this forms an orthonormal basis for H. Every continuous function in H is a combination of these functions. Here the coefficients can be found very easily through the dot product. Similarly, here the coefficients can be found through the inner product. That they are those an and bn formulas. Now let us see parallelogram law. That is norm x plus y the whole square plus norm x minus y the whole square is equal to 2 times of this one. The proof. Take the left hand side, norm x plus y the whole square plus norm x minus y the whole square. This is, if we expand this one, we get inner product of x plus y comma x plus y. For this one, we get inner product of x minus y comma x minus y. If we expand this one, we get inner product of x comma x and x comma y. After that, inner product of y comma x plus inner product of y comma y. Similarly, if we expand this one, we get x comma x, x comma minus y comma x, minus y comma minus y. Inner product of x comma x plus inner product of x comma minus 1 minus y. So minus can be taken out. X comma y, and again minus can be taken out. Inner product of y comma x, and minus into minus plus, so inner product of y comma y. Here see this minus of x comma y and this plus x comma y get cancels. Minus y comma x plus y comma x get cancels. So this is norm x square, norm y square, norm y square. So we get 2 times norm x square plus norm y square. Why this is called parallelogram law? See here, suppose this is an x vector, this is some y vector, it is x vector. So this is also x vector, right? And what is this one? This is x plus y. This is x plus y. So here see, this is x minus y vector. This is x minus y vector. X minus y vector. This is x plus y vector. Parallelogram law says that this distance plus sum of the diagonal distance is equal to 2 times sum of the sides distance square. This is called a parallelogram law. Now let us see one more. Next one is Pythagorean theorem. If x and y are orthogonal, then norm x plus y the whole square is equal to norm x square plus norm y square. See here, this is x, assume that this is y, and then this is x plus y. So then this square is equal to this square plus this square. This is y, this is x, this is x plus y. Pythagoras theorem says that if it is perpendicular, if these two vectors are perpendicular, then this theorem holds. Similarly, here also it holds. What is the expansion of this one? Take the left hand side, norm x plus y the whole square, that is equal to inner product of x plus y comma x plus y. The expansion is inner product of x comma x plus inner product of x comma y plus inner product of y comma x plus inner product of y comma y. But these two are orthogonal to each other, so this will be 0 and this will be 0. Hence we get norm x square plus norm y square. So this is called Pythagoras theorem. Similarly, suppose this is an inner product, and suppose this is another one inner product. This is one inner product, and this is another one inner product. Then the summation also will be an inner product. Try to prove yourself, and let us see one more thing. Now let us see one more thing. Let V be a vector space over the field F. Field may be C or R. Now we define a new function. See here, norm from B to R such that if this one such that norm x is greater than or equal to 0 for all x, and norm x is equal to 0 if and only if x is equal to 0. Second thing is norm cx is equal to mod c times x, mod c times norm x, where c is a scalar in f. The third condition is norm x plus y is less than or equal to norm x plus norm y. For all x comma y in V and c in f, then this one is called a norm in V. And see here, V is just a vector space over the field. You may define any function on V to R such that these three conditions should hold. Norm x must be non-negative and 0 only if x is 0. Norm cx is equal to modulus of c into norm x, and norm x plus y. The triangle inequality should hold. Then we call this is a norm, and we call this is a norm linear space. Is a normed vector space. Or simply normed linear space. See here, suppose V is a vector space, and suppose there is some function like this one that makes this as an inner product space. From this we may deduce the norm. What is the norm? Square root of inner product of x comma x. We may deduce the norm, but here without any inner product directly we may arrive at some norm. But here the unfortunate thing is, for some norms there is no corresponding to that. For some norm there is no inner product. That means we are able to define some norm on V. Corresponding to this norm, there is no inner product on V that actually induces from that. That means from that norm we could not get this. From that inner product we could not get this norm. What I am saying is, unfortunately, for some norms on V, there is no inner product that gives the same norm. There are some such vector spaces are there. Now let us see in the next session, let us see Gram-Schmidt orthogonalization process, which is so important. Before that, let us see a few more theorems and then Gram-Schmidt orthogonalization process. Let us see. Thank you.